Hi, I'm Ed Sperling. I'm the editorial director of Low Power Engineering. I'm here with Pravin Madhani from Mentor Graphics. How was that for messing up your name?
Yeah. How are you, Ed?
Good. Good to see you.
See you.
Place and route was considered sort of one of these secondary sort of boring areas, but as we start getting down into 20 nanometers, as we start getting into stack die, suddenly place and route becomes a completely different type of problem. There are all sorts of new issues showing up, a lot of physical effects, crosstalk, electrical interactions. What are you seeing as some of the problems there?
So, Ed, you brought up a very nice point here. At 20 nanometer, what's happening is you have a confluence of two things happening. You're getting a large capacity. Now designers are able to put 1 billion gates of logic in a die, and you have a lot of manufacturing issues coming up. As we go to 20 nanometer, there are a lot of multi-patterning issues, double patterning, triple patterning, and all this, along with people looking for better performance, better power, better area, is creating a lot of challenges for place and route. And what we are seeing right now for 20 nanometer is the biggest issue we see is in the area of exploding, scenarios, corners and modes, along with the multi-patterning. The combination is creating a situation for designers to really handle the complexity well.
What happens if lithography does not get to where we need it to be? So EUV has been under development now it's been promised at 28 nanometers, it's been promised at 20. It's looking even doubtful to be commercially useful, even at 14 nanometers. What do we do in between? What happens on place and route? Is it just a matter of more restrictive design rules, or are we now talking about potentially changing the whole dynamic here?
So what the foundries are doing is to compensate for the issue of EUV is have moved to this multi-patterning. So what they're doing is they're using double patterning as a way to solve the challenge. And what that means for place and route is create more restriction in the route. The entire system has to now support 20 nanometer, which means you have to support coloring and routing, coloring in placement, coloring in database, and extraction. So the place and route system is handling that very well, and the systems are now ready. Mentor Olympus can handle the entire 20 nanometer gamut when it comes to handling the multi-patterning.
Does it get worse as we start stacking? I mean, we're starting to deal with now things, we're dealing with not only 3D transistors, but potentially 3D die on die and die on wafer, wafer on wafer.
Right. It gets challenging from a couple of perspectives. It gets challenging in terms of how do you test the thing, right? Because now you've exploded the problem of testing this, right? Second problem it happens is how do you ensure the integrity of performance when you go across die? And this is where Mentor Graphics has a complete solution. We are uniquely positioned because we have always been playing in the packaging level. We've always been playing in the board level. And with Olympus, we have a complete support at the chip level. So we have a complete gamut of technologies for 3D ICs at chip level, at package level, and at the board level. And integrated cockpit really helps the customer, address that.
Do the pieces start breaking down though as we start getting into say 14 nanometer with triple patterning? Can you still do it the same way, or do we now have to start thinking about, oh, maybe this isn't the right method, maybe we do have to start adding in some new techniques?
It's a very good question. What so far we have heard from customers, we're already working with some customers on the triple patterning. They feel that they will be able to manage at least the 14 nanometer node with a little bit more restriction on the rule side by doing a very unique way of doing coloring for triple patterning, and changing the design rules in terms of restrictions. Beyond that, we're not sure. At 10 nanometer, we think there may be situations where people may have to completely rework the entire system.
Do 3D transistors as opposed to the 3D stacking, does that affect how the layout is done? Is there any change there?
So far, from a layout perspective, there is not going to be a major changes because we work through the pin axis, so everything is encapsulated in a library, and so we just have to ensure that we get to the right pin axis to the thing. But clearly from a manufacturing perspective, it is going to become a lot more challenging problem.
One of the other pieces that gets challenging here is as we start getting into multi-core and mini-core, we start dealing with all the pieces that have to be put in around the cores in different places than they were in the past. Are the rules that are set up in the past, will they still apply, or do we now have to start changing some of them as well?
So in case of multi-core, what the designers do is basically it is divide and conquer. So they would start working on each individual core, make sure that they work right, and then put the whole system together and ensure that the system achieves the performance they're looking for. So what you have to worry about is things like synchronized optimization is another technology we have, where how do you make sure that if you have one master, it still remains the master and doesn't change with every child. So there will be some technologies needed to ensure that you can do this very efficiently, but as of now, the industry has tools available to manage this. You're already seeing a lot of multi-core chips out there. The latest one of our customer, NVIDIA, we're working with has a 4-core Tegra processor out there. So you are seeing customers already doing a lot of multi-core, and the industry has tools ready to do that.
Will the change in materials change in things like moving more things concurrently up to the front part of the design, as well as dealing with them later on, which is what we've always done in the past, is sort of a linear flow. Now it's becoming more of a concurrent flow. How does that affect what's going on in place and route?
Very good question. So what happens with, when you go to FinFETs and materials like FDSOI, now you have more restriction requirement for the performance. And so the place and route has to start taking into account those scenarios of, there'll be different kinds of VT libraries you'll have to deal with. There'll be different rules you'll have to deal with. And you'll have to encapsulate concurrently along with your area and the capacity and the performance needs. And so far we have been able to create technologies, working very closely with our foundry partners to address these issues very efficiently inside the place and route domain.
Pravin Madhani, thank you very much for your time.
Thank you, Ed.